Hello, friends. Good
Yeah.
morning.
Good morning. Good morning.
Good morning, good afternoon, and good evening to all. Myself, Akshay Kumar, YA Chair, ASHRAE Chandigarh Chapter. Welcome to this webinar jointly organized by ASHRAE Chandigarh Chapter, ASHRAE Pune Chapter, and ASHRAE Deccan Chapter. I am sure you all are aware about ASHRAE. So, ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. This society uh, is seeking to advance heating, ventilation, air conditioning, and refrigeration system design and construction. ASHRAE has more than 57,000 members in more than 132 countries worldwide. Its members are composed of building services engineers, architects, mechanical contractors, building owners, equipment manufacturers, employees, and other concerned with the design and construction of HVAC and R system in buildings. The Society fund research projects, offers continuing education programs, and develop and publishes technical standards to improve building services, engineering, energy efficiency, indoor air quality, and sustainable development. So, if you are ASHRAE member, then it's a very good. If you are not, then please be a part of ASHRAE by register yourself at online at ashrae.org. Now, again, I welcome to this webinar. So today is our 21st webinar on sustainable infrastructure for communities. Now, uh, ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. Now, moving further. Now, I would like to introduce the ASHRAE Distinguished Lecturer, Mr. Daniel H. Nell. He's a today's presenter and he's a professional engineers, fellow ASHRAE, fellow AIA. He's a certified building energy modeling professional and he high performance building design professional. He's from USA. Now moving to the explained. So this is a full biography of the Mr. Daniel H. Nell. Mr. Nell is a graduate of Princeton University, Cornell University. He is a registered architect, a professional engineer, an ASHRAE Life Fellow, a fellow of AIA, a lead fellow, a certified building energy modeling professional, high performance building design professional, and a certified passive house consultant. ASHRAE activities include the ASHRAE Advanced Energy Design Guide Steering Committee, chair of SPC 227, the Passive Building Standard, the Building Energy Quotient Doc, and Oversight Committees, and TC 4.7. He helped author the 30% Advanced Energy Design Guide for small office building, small retail buildings, roadside lodging, and small warehouses, and the 50% AEDG for medium office building, medium and big box retail buildings and grocery stores, and the zero energy guide for K-12 school, small and medium office buildings and multi-family residential buildings. He was recipient of the ASHRAE Distinguished Service Award and New York chapter ASHRAE Distinguished Service Award. He has been a faculty member at the School of Architecture at the University of Pennsylvania, Princeton University, Cornell University, and Columbia University. Now, I want to do a later announcement. The recording of this webinar will be uploaded on our YouTube channel. Please subscribe our YouTube digital channel, ASHRAE Chandigarh. And the question and answer will be done at the end of this session. You can ask your questions by typing in chat box, and same will be answered at the end by speaker. Now I request to Mr. Null, please presentation your presentation. Over to you, sir.
Okay, I saw the note to share my screen, but it did not allow me to select which screen to share.
You may just share the presentation screen. That the presentation here in the PowerPoint. Yes. Can you please open it? Yeah. Yes. Yeah. Yes. Here it is. You can select it. Yes.
Okay, can you see that? Wait a minute, let me switch this.
Yes.
All right. I'm sorry, the PowerPoint only will display on my second screen. So when I hit this, it goes to the second, and you're seeing the secondary screen, are you not? Not the first
Yeah.
screen.
No, first screen. We are able to see both the screens.
No,
And second as
we're
well.
just able to see the first screen. What you'll have to do is try to, just stop sharing the screen and restart sharing your screen and see if it is if it asks you.
Yeah, I think
Which
that's a
screen
good
to
idea.
share. Or in your laptop, if you could just change your setting to duplicate the screen, then the second screen will not appear.
No, there is no duplicate option.
So,
Yeah, you can go to the display settings and then see if it allows you to duplicate. That's there on the top.
Okay, on top, view.
Display settings. The center of the
Instead,
screen
you
on the
can
top. Just besides the end slideshow.
What to do? I'm sorry.
Yeah, would be better if you can use the PDF version of this file.
Okay, wait, did this do it? I didn't see it. No idea of what to do for this.
Better to use PDF version of this file.
I'm sorry, I can't hear you very well.
Yeah, better to use PDF version of this file. PDF version. PDF.
No. Okay, I'm just going to do it this way since I can't, and rather than, is this okay?
Yeah, Mr. Dan, we are not able to see your screen. Can you please share your screen again?
Okay. Can you see my screen now?
Yes, yes, yes. It's
Okay,
better.
so rather than use PowerPoint in the projection mode, I'm just going to use it in the standard mode because I can't get it to project. It always projects on my second screen, and I could not figure out how to make this webinar share my second screen rather than my first screen. So I'll just do this, okay?
Yeah.
All right. Sorry for all of this confusion. It's these are different times, and we're all learning new skills. And unfortunately, I have not learned all the necessary skills for using GoToMeeting. So I'm getting pretty good at Zoom, but this one I'm not so good at yet. Anyway, the topic of today's presentation is sustainable infrastructure for green communities. I'm the presenter. This presentation is accredited for both American Institute of Architects continuing education and GBCI continuing education. The number or the for getting American Institute of Architects accreditation is right here. This shows that ASHRAE is a registered provider. This is also approved by GBCI. So the course ID is right here, and you can self-report on the GBCI website to get 1 hour of general continuing education credit for this presentation. These materials are copyrighted. The course description. Community planners have the opportunity for significant reduction of the environmental impact of human activity. Communities can be vital, complex ecologies that obtain maximum use of consumed resources while minimizing waste discharge. These goals are best achieved by exploiting the synergies among the separate infrastructure systems while obtaining multiple benefits from each conservation strategy. For example, greenways can provide not only pedestrian pathways, but also management and cleansing of stormwater runoff. Co-location of neighborhood scaled power, thermal, and wastewater treatment plants allows the byproducts of each system to be used as resources for the other systems. Pursuing these issues at a community level addresses issues at the most effective scale. Renewable energy production, on the other hand, is best handled on a regional scale so that sites can be selected for most effective harvesting of the resource. When these strategies are pursued in a single building, both conservation and economic effectiveness are often seriously diminished. The learning objectives for this course. At the end of the course, the participants will be able to recognize scale issues in the implementation of sustainable and alternate energy technologies and community development planning. Analyze potential synergies among various community infrastructure systems and integrate infrastructure systems with physical plans to maximize sustainability. Develop conceptual strategies for water and energy efficiency at a community scale. Recognize issues related to the role of community planning for global sustainability. Our ASHRAE slides. Urging you to complete the distinguished lecturer event summary critique at the end of the presentation. It's available online, I believe. And urging you to volunteer for ASHRAE. What is the scale of this opportunity for sustainable infrastructure? If we look at today's buildings and cities, they They create 30% of the global greenhouse gas emissions, 33% of the global resource consumption, 12% of the global fresh water use, 40% of the global solid waste production, and 10% of the global workforce is employed in urban areas. Urban areas present the opportunity to design not just the architectural solution, but the architecture of how to get to the solution. This requires a strategic mindset applied to systems thinking at the scale of the city. We look at the process of urbanization and how it's proceeding. 120 years ago, the population of the Earth was 1.7 billion, and only 10% of the people lived in urban areas. When we look at the projections for 2050, we see that the projected global population is 9 billion people, and 75% of those people will live in urban areas. We can characterize the 21st century as the urban age. Metro regions are 2% of the world's surface and generate 80% of the world's wealth. Over 5% of the world's population live in 23 megacities around the world, each with population of more than 10 million persons. There are now 400 cities with populations over 1 million. A century ago, there were only 16. Greater Mumbai has more people than Norway and Sweden put together. Sao Paulo is the same size as Australia. These statistics are in fact old, and in fact the process of urbanization likely has proceeded even farther since these statistics were generated. Global population will grow almost a third by 2044 to 9 billion people. That many people will need far more resources than exist on the planet. Global energy demand is expected to soar 44% in the next 2 decades. In 15 years, 1.8 billion people will live in regions of severe water scarcity, and 2/3 of the world population will live in areas of stressed water conditions. Traffic is a global problem. Many of the world's cities are completely stifled by automobiles attempting to get from place to place their daily travels, commuting to work, shopping, etc. The problem is that our non-renewable resources are decreasing as we use them up, and we're going to need to rely more on renewable resources to meet our needs. So when we think about the process, too often the wrong process is followed. We need to identify opportunities, not specific solutions. Too often, individuals come forward with, I know the way to save the world, and this is it. This is the specific solution. We need to keep an open mind. There will not be a single specific solution that will save the world. We need to emphasize the goals and not the means. Too often, we become fixated on a particular pathway and lose sight of the goals that we're trying to achieve. We need to emphasize strategies, not technologies. So often we hear people say, well, we can fix it all by everyone going solar. Well, solar energy may be a part of the solution, but it is not the single solution. So we need to look at strategy. The strategy is to reduce global greenhouse gas emissions, to focus on various types of renewable energy, and not to fixate on a single technology. And we need to find synergistic, multidisciplinary design alternatives. The solution for the world's problem will not be a single solution. It will be, in effect, sort of the death by 1,000 cuts. A number of different individual strategies working together in a synergistic fashion to create a better world. The goals, I think we can all agree on the goals. We're looking at the creation of livable, uplifting human environment for all of the world's citizens. We're looking at the restoration of habitat, restoration and renewal, so that the natural ecosystems can continue to maintain the world's environment as we have grown in and which we need for our survival. Obviously, we need to look at carbon emissions reduction. We need to look at recharging the aquifers around the world. We need to create clean, healthy watersheds. We need to look for optimized infrastructure support, and we need to create economic value. As I said, strategies, not technologies. So strategies include dense building and extensive green space, pedestrian accessible amenities, transit pedestrian accessible work to home, solving the last mile problem for urban transit, community-centered utilities if possible, optimized renewable energy sources, energy efficient individual buildings, utilization of non-potable resources. I'm going to demonstrate that much of the water that's used by human beings doesn't need to be drinkable. Stormwater management with detention and percolation to renew the aquifer, and efficient utilization of solid waste, treating solid waste as a resource, not as a plague. We need to recognize the synergies, the interlocking cascading systems, how green space, stormwater management, and non-potable water utilization interact and support one another, how dense building, pedestrian circulation, and transit utilization influence and amplify one another. Looking at how community scale utilities, particularly wastewater treatment, enable greater utilization of non-potable water resources. Look at community and building energy planning, community scale utilities, and optimized renewable energy sources and how they amplify one another. One of the problems that we have is we often look at the wrong scale for implementation of some of these solutions and technology. So for example, on a regional scale, offshore wind farms are very effective. Photovoltaic farms are solar thermal generation. Intercity fast rail to supplant airplanes and automobiles. On a city scale, waste pyrolysis plants with carbon char sequestration, real-time energy pricing for market response load management to enable our electric grid to better respond to the needs of its customers, and urban transit to avoid the need for automobiles in the urban center. On a neighborhood scale, looking at local wastewater treatment with effluent irrigation of parks and provision of cooling tower makeup for district cooling. Mixed-use zoning to improve pedestrian access. And on a building scale, look at things like microturbine cogeneration for domestic hot water. Here's an example of a community-scale photovoltaic system, a large PV system on top of the Georgia Tech Aquatic Center, providing far more electricity than is needed by that particular building and feeding it back into the local grid. Other regional scale wind energy generation systems. The problem is that too often we try to implement these systems on the wrong scale. So some of my clients in New York City say, well, you know, I want to put photovoltaic panels on the spandrel of my building, of my high-rise building. Problem is that there are other high-rise buildings in the neighborhood, and they cast shadows on your building. And also, when you locate at 40 degrees north latitude, your photovoltaic panels in a vertical orientation, they produce on an annual basis about 30% less energy than they would if they were optimally configured. So sloping, facing south and at a 40-degree slope above horizontal. Also, we get clients that say, I want to put a wind turbine on top of my high-rise building. Once again, not a very good utilization of capital. So I tell these clients what they should do, instead of put a photovoltaic panels on their spandrel panel of their building, they should put a sign that says, my PV system is located on top of a big warehouse over in New Jersey where it ought to be, or my wind turbine is located in the Long Island Sound where it gets better wind contact and creates more energy. So we look at transportation in an urban context. This is a study that I did a number of years ago, looking at density versus sprawl, looking at transportation energy use and comparing it with energy use in the building. So what we're comparing here is a high-rise building in an urban center with an office park in a suburban context, with the idea that the commuting of workers to the urban center occurs with the mass transit, whereas the commuting to the suburban office park occurs with individual automobiles. So if we look at the energy consumption of the buildings, the energy consumption of the suburban office building on a per square foot basis is approximately the same as the energy consumption of the high-rise building in the urban center. Clearly, the high-rise building has more energy use for elevators, but on the other hand, it has less of a heat loss through the roof and heat gain through the roof. So they're approximately equal. But if we look at the energy consumed by the workers going from home to work every day, we see that the urban center building, the energy consumption for commuting is slightly greater than the energy consumption for the building itself. But for the suburban office building, the energy consumption is almost 6 times as great as the energy consumed by the building. And these are the assumptions that the commuting round trip is 50 kilometers. It's a diesel bus, which consumes, this is for the urban transit, 1.7 kilometers per liter of fuel, and there are 20 passengers on the bus. And in the office building, we have 300 square meters per person, occupying the building 252 days per year. For the suburban office, same distance commuting, but it's in a private car that gets 6.5 kilometers per liter, but only one person, same occupancy. So solving the issue of urban transportation involves how do we deal with the last mile, that is, and the first mile. So we have in many cities solved, shall we say, the urban transit problem with subways and trams and electric buses and all sorts of things like that. New York City has a terrific subway system, as do Atlanta in the US, Washington, D.C. But the problem is the first mile, which is getting from your home to the subway, and the last mile, which is getting from the subway to your place of business. And that is the real problem, and that is where we are still seeking a solution. This last mile problem also applies to the distribution of goods within the urban center. Too often in lower Manhattan, we see tractor trailer trucks trying to navigate the very narrow and constricted streets there, when in fact, and generating lots of diesel fumes, when in fact that last mile of delivery should be occurring with small electric urban distribution vehicles. The idea then would be to essentially remove all cars and all internal combustion engine vehicles from the urban center. Energy. We have our community energy issues. We need to be very specific when we identify sources, because some of the things that we think of as sources are not sources. Electricity is not a source, it's a product. There is a source that makes electricity, and that source might be the sun, the wind, or hydro or wave, which is indirectly solar. It could be nuclear, it could be fossil, it could be biodiesel, which is of course indirectly solar energy, or it could be geothermal. And by this I mean real geothermal, not ground coupled thermal storage. We need to look at how we transport energy, because in almost all circumstances, the source of the energy is not co-located with its end use. So we have, sometimes we have connected storage, which would be natural gas pipelines that go directly into our buildings. It could be electricity, where wires go directly from the generation source, the power plant, to the end user, the building. Or it could be discrete transportation. So oil, a tank truck comes to your building and fills your oil tank. Or gasoline, where you drive your car to a gas station and fill it. And with the hydrogen solutions that we've seen, most of those involve for fuel cell automobiles or vehicles, discrete transportation, where the vehicle goes to a filling station and the tank is filled with hydrogen. We need to look at the issue of storage and of energy density. In many circumstances, we need to store energy because we need to disconnect the profile of end-use consumption from the profile of generation. And that's particularly true in the case of renewable energy, because most renewable energy sources tend to make energy when they feel like it, when the resource is available, when the sun is out, when the wind is blowing, when the tide is flowing, not when you need it. So you need to harvest that energy when the generation is available so that it can be used when needed. Also, when you think about it, when you have a discrete transportation of an energy source, you also need storage. So the gasoline tank in your automobile is a form of storage, as is the oil tank that might serve the heating plant for your building. When we look at the storage, energy storage, and the technologies that are available, we have batteries, capacitors that store electric energy. We have kinetic energy storage in the form of flywheels and things of that nature. Or we have potential storage, such as the pumped hydro, where a pump pumps water to a storage tank that's on a that is at a higher elevation. And when that storage is tapped, depleted, the water essentially runs downhill and turns a turbine to generate electricity. And of course, liquid and gaseous fuels are a form of storage. What we see is that when we look at the energy infrastructure, there are a number of conversions that occur, one form of energy to another, from the source to the end use. And we need to look at that conversion efficiency. Cogeneration and district thermal sources are clearly one part of the solution to our energy problem, because we are able to tap the waste heat from the generation of electricity to provide thermal needs. So this is a very quick analysis of a combined heat and power plant with a standard sort of solution whereby the waste heat from the electric power generation is wasted, and yet our need for thermal energy is generated by a separate boiler. And so we can see that there's a significant increase in efficiency by utilization of the waste heat from the generation of electricity. When we look at, in the United States, our utilization of energy, and this is a diagram from the year 2018, the US energy consumption was 101,000 quadrillion BTUs of energy. And we look at how energy is used in residential, commercial, industrial, and transportation. And then we look at the rejected energy. About 2/3 of the source energy that is consumed in the United States is actually rejected. And that's rejection from heat engines, which are used to generate electricity, and rejected heat in a heat engine is a necessary part of the thermodynamic cycle. It's also the rejection of energy for heat engines that are used in transportation. You know, gasoline engines, diesel engines, other types of internal combustion engines, even steam engines necessarily have that thermodynamic requirement for rejection of heat to create work. In industrial, we have the same issue. So the point is that some of the utilization of energy in these sectors, residential, commercial, industrial, not so much transportation, is in the form of heat. And we could be, if we were configured correctly, tapping this rejected energy in the form of heat to meet our thermal heat requirements. So what we need to see in the future going forward is really kind of an internet, shall we say, of energy. Most of you probably are not old enough to remember time-shared computing back in the day, you know, with IBM 3030 mainframe computers, and the distribution network for computation was entirely radial. That is, you had dumb terminals that connected directly to the mainframe, and there was a time-sharing sort of arrangement whereby the terminals were served on a sequential basis. Unfortunately, when the mainframe went down, everybody lost computational resources. Today, we have the internet. where computational capability is spread around a network. There are multiple nodes. There are multiple connections between the nodes, and you can lose a major node and no one ever notices the difference because the network shifts to take up the slack. And that's really what we need for our energy infrastructure. Today, unfortunately, in most countries, the energy infrastructure is sort of the energy equivalent of mainframe computer time sharing. We have central energy generation stations, electric generation plants, and when they fail, they can start a calamity, and we experienced that on the East Coast about 15 years ago with the Great Blackout, where one power station having a problem somewhere in Indiana started a cascade which shut down the entire northeastern quarter of the United States. If a community energy infrastructure of this nature, as shown on the screen, were implemented, that would not happen. We would have wind generation stations, solar generation. We would have our combined heat and power. We would have waste to energy, and we would be locally utilizing the thermal resources from electric generation to meet thermal needs, and so on and so forth. And this would be a very robust infrastructure that makes best use of the resources that it consumes while minimizing the generation of waste. And an example from a number of years ago, a fuel cell at a casino here in the United States that uses local heat recovery from the electric generation process to meet local thermal requirements. A number of years ago, I was involved in a master planning effort in the Middle East, and we were proposing co-located local electric generation stations along with local wastewater treatment and local district cooling. And we were told that was not possible because in this particular large city in the Middle East, there was no natural gas distribution infrastructure, and that they preferred to have natural gas fired electric generation stations on the periphery of the city and to distribute over ultra high voltage overhead power lines this electricity, which was generated remotely, into the city. So we did a land use study for the various alternatives. So we had our extreme high voltage transmission lines with central generation. The overhead right-of-way required for these very high transmission towers into the city was approximately 540 meters wide. The cost of each of the 4 overhead circuits, 70 megawatts each, was $2 million per kilometer. The development value of the land was $122.5 million per kilometer for this alternative. So we have then the second alternative, which was underground electric. We have the underground electric corridor would be reduced to 100 meters wide. For a typical 4 circuit corridor, the cost would be $20 million per kilometer. So the urban land value is $250 per square meter. So the land released from moving from overhead transmission lines to underground electric would be $110 million per kilometer. And then we looked at underground gas distributed generation. So the urban corridor would be reduced to 50 meters wide. And for the typical 24-inch gas line, the installation cost is $250,000 per kilometer. And the land released was valued at $122.5 million per kilometer. So despite the fact that there was no natural gas distribution infrastructure in this large Middle Eastern city, the actual cost of bringing gas in to distributed local cogeneration plants was far less than the cost of building the generation plants on the periphery of the city and then bringing in the power by overhead transmission lines. By the way, the location of the electric generation plants of the periphery precluded the utilization of the waste heat from the generation process for things like domestic hot water and low pressure desalination. When we look at our distributed generation assets that we might utilize, we see that they have different characteristics with regard to efficiency, part load performance, size, the amount of space required, the install cost, the operations and maintenance cost, the capacity, the fuels that they use, the noise, the NOx generation, and what is the temperature at which they reject heat, which leads to what different types of end uses the waste heat can be put to. So what we can say is that when we are considering a combined heat and power, a distributed generation plant, we can look at all of these characteristics to decide what particular technology is appropriate for what particular application. This is just a general outline, diagram of a combined heat and power plant that I worked on in China several years ago, looking at engine generators for electricity, very high efficiency engine generators, and then a utilization of absorption chillers and for making cooling. The next issue in community infrastructure for green cities is solid waste management. Excuse me. We look at the generation, for example, of plastic wastes in 2010, and we can see that there are a number of countries, including mine, which generate excessive amounts of plastic waste, unfortunately, much of which goes into the ocean. What we need to do is we need to invert the waste management triangle. Currently, source reduction of waste has the smallest emphasis. Next, we go to recycling and composting. Then we have conversion technologies, and finally, the major solution for solid waste in the United States is landfill. Just basically burying it, getting rid of it. And what we need to do is we need to invert this triangle and concentrate on source reduction, then recycling and composting, then conversion technologies. Conversion technologies are essentially waste to energy, and then with landfill as the last resort. We need to basically develop an urban waste management strategy to enable the separation of the streams of waste for different end uses right at the source of generation, so that they don't have to be separated later, which is a much more arduous task. I was involved a bit in the planning for Masdar City, which developed, at least initially, a comprehensive waste management strategy, wherein 50% of the waste stream would go to recycling, 17% would go to composting. Some of the non-recyclable would actually go to waste to energy after the hazardous waste had been removed, with the idea that the city develops into a zero waste city. Water. We have here the natural water cycle. Unfortunately, water in a form that is suitable for human utilization represents only a very small part of this water cycle. Typically, we utilize water from underground or from freshwater surface assets to meet our water needs. But the great majority of water on the planet is stored either in oceans, where it is saline and has to be treated before it can be used by human beings, or in the form of water vapor in the atmosphere, where it is not really usable. Much of the water that human beings use doesn't have to be potable. We need to understand what potability means. Potability is not really a chemical definition of the amount of pollutants in the water. What it is a legal definition that there is an authority that is legally responsible for ensuring that human consumption of a particular water resource will not result in harm. So we have instances in the United States, for example, in Flint, Michigan, where there was quote unquote potable water, which had been determined to be harmless by the local water authority, but which was slowly poisoning the residents because of its lead content. Unfortunately, that local authority is now subject to all kinds of liability because they failed in their mission to ensure that the water could cause no harm. So we have our alternative sources of non-potable water available in the city. So we have the city water as a comparator, which has no debris, a very low suspended solids, very low dissolved organics, very low dissolved organics, and very low microbia. And then we have different resources that are available at different scales, and they have different characteristics with respect to the various kinds of contaminants that they contain. So we have something like HVAC condensate, which is no debris, very low suspended solids, very low inorganics, organics, and microbia, particularly if the cooling coil is irradiated with UVC. There will be virtually no microbia at all. This is essentially distilled water. It is very pure, but it is not potable unless you, as the building services engineer, want to deem this water to be fit for human consumption and take on the liability in case something fails in the supply chain for delivering the HVAC condensate to the user. However, if this water is not to be drunk or not to be used for personal hygiene, it is very pure and can be used for many different end uses within the building. And similarly, the other types of non-potable sources within the community have different types of use. So we look at matching the sources with the end use. So our city water, primarily ingestion, secondary use personal hygiene, HVAC condensate, we can use that for flushing toilets. We can use that for domestic hygiene, washing clothes, potentially washing dishes. Stormwater, use it for flushing, cooling tower makeup. Stormwater on grade, irrigation, wet wash water could be used for irrigation. If it's not stored, unfortunately, wash water, if it's stored because of its relatively high dissolved organic content, tends to grow bacteria and become fetid, to become smelly, in fact, to become effectively black water. So if you use wash water in the context of trickle irrigation, then in fact, that could be its primary use. Cooling tower blowdown has a lot of contaminants, but it can be processed with reverse osmosis to produce very high quality water that can be used for things like flushing and cooling tower makeup. Treated black water, that is sewage treatment, potentially can be used for cooling tower makeup and for irrigation. And what we need and what we want to have is an improved water, urban water cycle where there is no waste disposal into the surface water bodies, and whereas the various non-potable end uses are, for the most part, met with the non-potable resources that are available within the community. One of the community scale treatment alternatives is so-called local wastewater treatment, where we have very small local wastewater treatment stations that enable the utilization of the treated sewage effluent for local uses such as irrigation and potentially flushing. The DWATS, Decentralized Wastewater Treatment System, is the prime example of this, which can be implemented on a neighborhood scale, resulting in significant reduction in the utilization of city water for human use. And utilization, this is a DWATS finishing bed, a local park amenity that is entirely irrigated from the treated sewage effluent from the DWATS. And this is a case study for water optimization and reuse of non-potable resources. The Godrej headquarters in Mumbai. I worked on this building, and particularly on this. This was the design comprehensive water harvesting system to try to make use of all the different non-potable assets on site, including harvesting of the foundation drain water and treatment with a reverse osmosis system, because the foundation drain water was relatively saline, because this particular project is located pretty close to the mangrove swamp, which is saline water. Also harvesting through the reverse osmosis system of the cooling tower blowdown. It included a packaged sewage treatment plant and harvesting of roof stormwater and with allocation of these different assets to the appropriate end use. These were our projections for the design usage, a total in the building of about 360,000 liters per day, and we were proposing that that would be met by about 125,000 liters per day from the city, and the rest of the energy consumption, or excuse me, of the water consumption in the building for non-potable uses would be met by these various non-potable assets. Unfortunately, the design changed at some point during construction documents. The reverse osmosis treatment plant was deleted. There was some downsizing of the rainwater harvesting tanks, with a result, however, of a significantly greater utilization of potable water from the city, but still about 40% of the water that's used in the building comes from non-potable resources, from the black water treatment, from the stormwater harvesting, etc. There is a guideline for green communities, the lead for neighborhood development, which has been evolving to recognize the synergies between the various infrastructure systems in the community. And so here are the conclusions that I've arrived at. It's possible to achieve dramatic reductions in carbon footprint by optimizing pedestrian and mass transit at a community scale. Community scale power generation enables doubling of efficiency of plants through waste heat utilization. Local siting of wastewater treatment plants provides a valuable source of water for non-potable usage. Greenscape integrated into the urban environment is a powerful strategy for optimal stormwater management. Community design is a powerful tool for environmental responsibility. The bottom line, the world will be saved not by building millions of LEED Platinum buildings, but by building thousands of sustainable communities. Thank you. So I don't know how we're handling questions, but or whether we have time, but if we do, I think, let's see if I can enable the chat here so that I can see any questions that might be asked. Thank you.
Thanks, Daniel. That was a fantastic session. So I'm just looking at the questions here. Just a second. Akshay, Mani, are you available? Akshay?
Yeah, hi. One more.
Hi, Akshay. Can you help me out? I'm not seeing any questions in the tab.
I'm also trying to look at that. Let me just check with Mani once if he can.
I see he's offline. Okay, we'll just give him a
I'm
break.
just giving him give me a second. Yeah.
Yeah. So Daniel, I have a question myself. When you said the one of the ways to cut down carbon footprint is by having community, what do you call it, mass community, sort of pedestrian sort of outreach. So how does that exactly help in putting down the carbon footprint? Like what I'm trying to understand is when you're looking at the more number of buses or say trains and stuff, so wouldn't that also add to the carbon footprint as well?
The answer is yes. Increasing the number of buses does add to the carbon footprint, but if you look at the carbon generation per mile per person,
okay,
mass transit has a much lower impact than does utilization of automobiles. Automobiles carry only 1 or 2 persons typically, whereas a bus contains 20 or 30. And despite the fact that, let's say, the mileage rating of the bus might be 1/3 to 1/4 of the mileage rate of the mileage ratio of the automobile, if the bus is carrying 10 or 20 times as many people as the car, clearly that is a reduction in the total carbon footprint for moving people. That is, carbon footprint per passenger mile is much
Okay.
less with mass transit than with individual automobiles. New York City, for example, which has relatively low commuting by car and very high commuting by electric train and subway, has a very low carbon footprint for transportation compared with other cities in the United States that rely primarily on automobiles for transporting people between home and work, between home and shopping, between home and chores. And that is very much borne out by the data about the New York City carbon footprint. For transportation, it's very low because it relies primarily on electric buses, or excuse me, electric trains and subways for commuting.
Okay, so I think I have my answer here. So I'll just start to the questions by the contestants. We have first question is, why is the underground transmission so high? Underground transmission line is high, by Muhammad Sahid.
Wait, could you repeat that a little more slowly? I couldn't quite pick it up.
Yeah, why underground transmission line is so high?
Okay, so I'm not an electrical engineer. I'm a mechanical engineer. So there's something about currents that are induced in wet soil by the high voltage alternating current in the underground line, which causes that underground line to be expensive. And I don't understand it. That's not my area of expertise. We just got an estimate for the cost per kilometer of underground line. The overhead line, of course, includes the towers and the conductors. The underground line did include the excavation and the material for the line itself and putting it in place. I guess because of the ground shielding, the right-of-way for the underground line was much narrower. Clearly, people don't want to live or work underneath ultra high voltage electric distribution lines. There's some funny things that may happen there in terms of induced currents and that sort of stuff. Once again, not my field of expertise, but the assumption that we made was that the corridor for the overhead line would conform to electric utility standards. The corridor for the underground transmission line was once again in accordance with electric utility standards, and the estimate for the actual construction of the electric lines, was done by our cost estimator based on specifications from the electric utilities.
Okay, so I'll move on to the next question. How do you advise for a house to be zero waste production, by Prashant Dubey?
So how do we make what zero waste production?
A house.
A house. I don't think that can be done on on a house by house basis. I think that that's a community endeavor. Actually, it's more than that. It's actually an endeavor of an entire economy. So, as we said, the first most important strategy for dealing with the solid waste problem is to reduce the amount of solid waste that is generated. And primarily that is around packaging. And so we all consume products that are packaged. Some of that packaging is cardboard, some of that's plastic. We need to be much better about our packaging, making it either all recyclable or in some cases reusable. You know, when I was a little child, milk was delivered to our house in glass bottles that were reused. And so when we were done with the glass bottle, we put it out on our doorstep, and the milkman collected the empty bottle. It was taken back to the milk distribution plant where the bottle was sterilized and refilled, and then the milk was delivered, you know, the next day. So for a lot of reasons, that practice went away, but we need to think about, you know, what is the 21st century version of that practice? How can we reuse? Because reuse is much better than recycling, because recycling basically means that the material or the product, the packaging product, essentially will be reprocessed and made into a new form, which requires energy and I mean, we look at recycled aluminum. We have to, while we don't have the energy consumption of refining the bauxite into aluminum, we still have the energy consumption of taking the aluminum can and melting it so that that it can be made into a new product. Whereas if we had some type of packaging for liquid that could be just refilled, we would entirely avoid the energy consumption of reprocessing that packaging product. So that's actually a solution that involves the entire economy. But you know, from a house standpoint, let me just finish by saying, selecting your products according to their packaging, doing your composting, and being very diligent about separating what is recyclable from what is not is a good start. And then what we need to do is to make sure that the stream of potential waste that comes into your house falls more into the categories of reusable, recyclable, and compostable, and less into the category of the only thing we can do with this is put it in the landfill.
Okay, so I'll go to the next one. I'm seeing a lot of questions on the pandemic and how has it accelerated the growth of sustainable architecture, and if you can shed any light on that.
Wait, could you say that again?
Can you shed some light on the pandemic and whether it has accelerated the growth of sustainable architecture?
Okay, so has the pandemic accelerated, how has the pandemic accelerated the growth of sustainable architecture? Is that the question?
Yes, that is.
Well, I'm not sure. I think it's too early to say. I think the pandemic has definitely brought a focus onto the issue of indoor air quality. I don't know that that particular issue falls into the topic of this particular presentation, but it definitely falls into the issue overall of building sustainability. I've been doing work with some of my clients about looking at exactly how we can configure HVAC systems to minimize the potential for communication of disease vectors within the indoor environment, looking at airflow patterns within rooms, looking at what are ways that that we can use to remove pathogens from the airstream. So, you know, I think from that standpoint, that's a very immediate impact. I'm not sure how it's going, what are going to be the impacts, you know, going forward. I think there will be some. I'm not wise enough to know what they are yet. I'm only aware of the more immediate ones.
Okay, so the next question is, how would one incorporate sustainable communities in old cities where much of the infrastructure is already built on a non-sustainable model?
Okay. This is an interesting issue that came up. I was doing some work in Costa Rica a number of years ago, and Costa Rica has a real problem. They get all of their water from wells, and the water level is dropping at a very rapid rate. And so you go to their capital city, and you see why they get all their water from wells, because the city has no sewage infrastructure whatsoever. Basically, sewage from individual buildings comes out of the building in a trench and goes into a trench that runs along the side of the road. And that is both stormwater runoff and raw sewage. And it smells, and you know it's raw sewage. So a number of years ago, they decided to improve this structure. By the way, this sewage runs directly into the surface water features, which are basically the system of streams and the main river that runs through the city. So raw sewage is going directly into the river. And so as a result, the river is not a good source of water to meet the needs for the city. So they get all their water from wells. A few years ago, they decided to improve this system. And so they lined these trenches with concrete, which basically did two things, neither of them good. Number one, it removed the ability of the plants which were previously growing in these trenches to process some of the organic material out of the sewage stream. It also completely eliminated the possibility that some of the water would percolate through the soil and be cleansed by the natural filtering action of the percolation to provide some replenishment of the aquifer. So they were very at odds about how to deal with this situation, realizing that to deploy, to create the entire sewer infrastructure for the city would cost billions of dollars and would, or at least hundreds of millions of dollars, and would require years before they would get any benefit. However, we pointed out that deployment of a DWATS distributed wastewater treatment system on a neighborhood by neighborhood basis, essentially installing the natural cycle sewage treatment in the streets, underneath the streets, in caissons that would be excavated under the street and then paving back over and then collecting from individual neighborhoods would allow this process of creating a sewer infrastructure to proceed in a piecemeal basis, getting individual benefit as each step was finished. So the idea here is that to realize that, and for example, talking about let's say the plan for co-located district cooling, generation, and wastewater treatment for this Middle Eastern city, that could have been pursued on a neighborhood by neighborhood basis. So the idea is that when you have these integrated solutions, they can, to the extent that they are, and most of them are, appropriate at a neighborhood scale, they can be pursued on a piecemeal basis, taking neighborhood by neighborhood to create the improvement.
Okay, so I'll take this last question. Um, what is the major source of greenhouse gases, and how do we measure on infrastructure basis for green communities?
Well, the major source of greenhouse gases varies from place to place. So in many US cities, the majority of greenhouse gases are generated by transportation, which is cars, trucks, and buses, and that sort of thing, all of which are using internal combustion engines. In New York City, 70% of the greenhouse gas generation comes from buildings. And that's because, number one, New York City, for the most part, is so dense. And number two, much of the transportation is mass transit, and there's much less utilization of cars within the city limits of New York. So the individual solutions for reducing greenhouse gases is going to vary from location to location. So for example, I'm not familiar with cities in India and what are the primary sources for greenhouse gas generation in Indian cities. I think that's, you'll have to find that data and then try to craft solutions that address the very specific issues in each city. I know that in many US cities, for example, Houston, the issue there is transportation. It's cars. Everybody is going everywhere in a car, and typically there's only one person in each car. So they have a really big problem of trying to create a low greenhouse gas public transportation system, not only solving the issue of the major travel distances for the mass transit system, getting from the suburbs to the city center, but also the first and last mile issues, which is how do the people get from their homes to the mass transit station, and then how do they get from the mass transit station to their place of work when they get to the city. So the answer is, I'm sorry to say, it depends on where you are and how your city is configured, and what are the systems that are generating a greenhouse gas in your city.
Okay, so I think all of you can send your questions to Mr. Daniel. I think thanks, Daniel, for giving me an opportunity. So I'll hand it over to Akshay for taking it forward. Akshay, it's all yours.
Yeah, thanks, Anmol. Hello, everyone. I'm Akshay Pahade, CTTC Chair from ASHRAE Pune chapter. Hope you all had a great time learning from the webinar today. And thank you, Mr. Nal, for joining us today and giving us insights in the real-world challenges in implementation of technologies in community development and planning.
Thank you.
The examples you shared, especially in the context of energy and water, were exhaustive, elaborate, and yet easier to comprehend. From the basic principles to advances in technology, you covered it all and also gave insights in context of community development. I'm sure our attendees today have benefited a lot from this session. And also the question answer session was very insightful, and I hope that most of the questions were answered adequately. In case you have any more questions, you can get in touch with any of us, and we'll pass it on to our speaker for today. On behalf of ASHRAE Pune, ASHRAE Chandigarh, and ASHRAE Deccan chapters, I thank you all for joining us today. In case you missed any of this presentation, you can access it later at the YouTube channel of ASHRAE Chandigarh. Also, if you have any questions or queries regarding today's presentation or would like to join ASHRAE or get more information about your local chapter, please get in touch with any of us and we'd be glad to help. I would also like to extend the special thanks for the organizing committee today, CTTC Chair of ASHRAE Chandigarh Chapter, Mr. Mani Khanna, YA Chair, Mr. Akshay Kumar, CTTC Chair of Deccan Chapter, Mr. Anmol Prabhu and Mr. Anuj Gupta, the chapter presidents from Pune, Mr. Vikas Kotian, from Chandigarh chapter, Mr. Amardeep Singh, and from Deccan chapter, Mr. Sandeep Galhotra, and all others who have directly or indirectly contributed in making this session successful. I now declare that the session is concluded. Stay safe, follow necessary guidelines for social distancing, and take care of your health. Thank you, everyone.
Thank you. Bye.
Thanks, Daniel.
Thank you.
Take care all.